Hi there, Mr. Sutton here with the AB Calculus Chapter 4 Quiz 1 Review Solutions on Extrema. On this problem, we need to just identify each of these letters as being the x value of a relative max or min, an absolute max or min, or neither. Some of these could be more than one. For example, letter A, you could argue that this is neither of these things. Relative maxes and mins we tend to think of as being you're either increasing on both sides or decreasing to either side, and this is one-sided. And also it can't be an absolute max or min because it's not the highest or lowest point of the whole graph. But there are some people who would argue that if it's the lowest point in its immediate area, even if it's one-sided, that you could count this as a relative min. So I'm going to leave it up to you whether you want to say neither or relative min on this one, but there are people who would argue either way. Now choice B, or option letter B, this could be, you could say that this is a relative max because it is the highest point in its area. It is also the absolute max. It's the highest point for the whole graph. This is the only place that you could say is the absolute max. For C, this is none of the above. It's not the highest or lowest point in its area or for the whole graph, so that's neither. D, this is the lowest point for the whole graph, so you could call this the absolute min. There's nowhere else you could say that about. You could also call it a relative min because it also is the lowest spot in its immediate area. And then for E, this is not the highest point, but it is the highest point in its immediate area, so that's a local or relative max. R, this is going to be neither. It's not the highest or lowest point in any respect. S is a relative min. It's not the absolute min, but you can still say it's a relative one, lowest point in its immediate area. And then with T, we have kind of the same debate as we had at the other endpoint. T is not the highest or lowest point for the whole graph. It is the highest point in its immediate area, so you could make the argument that it's a relative max, but if you need two sides for a relative max, you could say this is neither. On this problem, we're asked if the extreme value theorem applies to each of these graphs and why or why not. So the extreme value theorem says that if you have a closed and continuous function, so a function that's continuous on a closed interval, then we're guaranteed to be able to find an absolute min and max on that function. So this first graph here, it is closed, it is continuous, so this is a yes because it is closed and continuous. The extreme value theorem would apply to this graph A. And that actually gives us a guideline for how these other ones break down. Graph B is a no because it is not a continuous function. Now, by the way, this doesn't mean that you can't find a max or min. It just means you're not guaranteed. On this graph, you certainly can find the max. It's right here. And the min looks to be maybe this endpoint over here. But we weren't guaranteed to be able to find it because of the lack of continuity. And that's the key on these. Now, for C, this is also a no because this one, although it is continuous between the endpoints, it is not on a closed interval. The endpoints themselves are not there. So this is not closed, therefore the EVT does not apply in this case. For this problem, we're trying to find the absolute max and min for this function here. Now just doing a quick check, since we have a closed interval, and this is a polynomial which is continuous, we're guaranteed by the extreme value theorem that we can find an absolute max and min. So let's go ahead and do that. Now whatever method you're using for finding max and min, it's going to involve finding critical values, which means we need our first derivative, f prime. So that's going to be 6x minus 12, and we need to see where that equals 0. It equals 0 if we add 12 and divide by 6 at x equals 2. And from here on out, there's different ways we could go. One way you could go, since this is the only critical value, you could do sign analysis around this, and if it turns out to be a local max, then we're guaranteed it's an absolute max if it's the only critical value. Same thing with the mins. But this won't get you both of the extrema. If you want to get both of them, then for sure you're going to need the candidates test, where we take the critical values and each of the endpoints and plug them in to the original function. Because really there's only two places that highest and lowest points can happen. Turnaround spots, in other words, places that critical values could represent, or endpoints. So let me go through and plug in 0 now to start this off with our candidates test. If I plug 0 into the original, that gives me back a 5. And the next point I'll plug in is our critical value of 2. Plugging that in, that's going to be, let's see here, this is 3 times 4, so that's 12, minus 12 times 2, that's 24, plus a 5. This is negative 12 plus 5, or negative 7. And then we have to plug in our other endpoint, 3. That's going to be, let's see, 27 minus 36 plus 5. So this is negative 9 plus 5, which is going to come out to negative 4. Now we just have to compare these. We've got our candidates. The highest of these is the only positive number, the 5 here, so that's going to be our max, our absolute max. And then the lowest one is this negative 7, so that's our min. For this problem, we want the absolute max or min of this weird rational exponential problem. Now you might recognize this function. If not, this looks kind of like a seagull. It looks like an absolute value, only it's more severe as you get closer to the bottom. It's like a curved V. Anyway, even if you didn't know that, we can do some analysis on this. So this is a continuous function. We are cube rooting things and squaring things, both of which are continuous kinds of functions. And we have a closed interval. That means by the extreme value theorem, we're guaranteed that we have an absolute max and min for this thing that we're going to be able to find. So let's go ahead, find critical values, and plug those in along with the endpoints to see what gives us the highest and lowest values. So for our derivative, we've got, using our power rule here, 2/3 x to the negative 1/3. And I'm going to simplify this a little bit, clean it up a little. So this could be written as 2 over 3 times the cube root of x. And the reason I like doing this is it's a lot easier now to see what kinds of x values are going to make this thing either 0 or undefined, because both of these types of things could be critical values. Now checking out what makes this 0. Since we have a constant in the numerator, no variables up there, there's nothing I can plug in for x that is going to make this fraction 0, because 0 is not ever going to be in the numerator. So this never equals 0. However, we have an x in the denominator, and if we plug 0 in for that, that'll zero out the whole denominator and we'll be dividing by 0. Therefore, f prime does not exist at x equals 0, and that gives us a critical value that we can now test. So we're going to test 0 along with our endpoints of negative 8 and 27. Now when I plug numbers into the original function, again, this is the cube root, and we're squaring the result of that, or squaring and then cube rooting. It actually doesn't matter what order you do it in. So f of negative 8, that's going to be cube root of negative 8 squared, and then we have this plus 5. So cube root of 8, that's going to be negative 2. Negative 2 squared is 4, and 4 plus 5 is 9. Let's go ahead now and apply this to 0. Now 0 is a little easier to work with because if you raise 0 to any power, you're automatically going to get 0. Unless you have a negative power, then you might be dividing by 0. But any positive power is going to give you 0 back, any combination of roots and whatnot. We still have that 5 there, though, so you have to add that in there. So f of 0 is 5. And then plugging in 27, so now we've got cube root of 27 squared plus 5. That's going to be 3 squared, which is 9. 9 plus 5 gives us 14. Comparing these, we see that 14 is the highest one, so that's our max. And 5 then is our absolute min. For this problem, given this function here, we want to find the intervals of increase and decrease for f of x. So if I'm trying to find out where f of x is increasing or decreasing, I need to know where f prime of x is positive or negative. So let me go ahead, since they gave me f, I need to find f prime. That's going to be 3x squared plus 6x, and then this negative 4 just becomes 0. And I need to solve for critical values to figure out places where f prime might be changing sign. So I've got a 3x, so let me set it equal to 0 first, and now I can factor out a 3x, leaves me with x plus 2 inside, and that's all going to equal 0 if x is 0, or for this parentheses if x is negative 2. Those are my critical values. I'm going to put those on a number line, which I will label with f prime here, and I'm going to do some sign analysis around these. So I've got negative 2 and 0, and now I'm going to test a number in each of these 3 intervals that I've split this up into. So I take a number to the left of negative 2, like negative 3, plug that into f prime here. I'll use the factored version. That's easier to figure things out with. So this is going to be a negative and another negative multiplies to give me a positive. Now a number between negative 2 and 0, like negative 1, that's going to be a negative times, let's see, negative 1 plus 2 is a positive. So negative positive gives me a negative overall. And bigger than 0, why not just try 1? That's a positive times a positive, which is positive. So looking at where my f prime is positive, I see then that I have f increasing on the interval from negative infinity to negative 2. That's one place f prime is positive. Union, so also on the interval from 0 to positive infinity. That's the other place where f prime is positive. And going the other direction, we see f prime is negative between negative 2 and 0. So f then is decreasing on the interval from negative 2 to 0. For this problem, given this function here, we want to find intervals of increase and decreasing for f of x. So if we're trying to find these intervals, we need to know where f prime of x is positive or negative. So taking a look at what they gave us, normally we would need to take a derivative to get f prime, but hey, look at this. They already gave us f prime. That's not a typo. They're handing you kind of the halfway point of one of these problems. So if you've already got f prime, all you have to do at that point is find the critical values and do some sign analysis. So this f prime is going to equal 0 when x is 4 for that first parentheses or 1 for that second one. So let me just set up a number line and test this out. So here's my f prime number line with critical values at 1. We'll just write these in order, so 1 and 4. Testing out something in each of these intervals, number less than 1, I think 0 is a pretty good one. Now when you're doing the sign analysis using this derivative up here, this squared parentheses, because you're squaring, whatever comes out of it is always going to be positive. And this 4 is obviously positive. So the only thing that's going to make any difference is going to be this x minus 1 parentheses, just to speed things up a little bit. So plugging 0 in then, 0 minus 1, that's just going to be negative. Now a number between 1 and 4, like 2. 2 minus 1 is positive. See how much faster that is? And then bigger than 4, let's try 5. 5 minus 1, still positive. All right, so I notice that my f prime is positive from 1 to 4, and then from 4 to infinity. Now there's two ways that you could write this. You could say that f is increasing on negative or positive 1 comma 4 union 4 comma infinity, and there are some people who would argue that's correct. You could also actually say that we're increasing on the interval from 1 to infinity. So it's kind of debatable whether you're allowed to include these values where the derivative is exactly 0. If the function is actually defined at this value, you're allowed to include it or not. If this value is not defined in the original function, then you couldn't include it. Now here we don't know what the original function actually is. There's ways that we could find it. Since the derivative is a polynomial, there's a pretty good chance the original was also a polynomial, but I'm just going to leave it like this, and this is perfectly fine. Now, one thing that's not debatable is that this function is decreasing on the interval from negative infinity to 1. Negative infinity is going to need a parentheses. 1 could get a bracket or not, depending on whether 1 actually exists for the original function. For this problem, given this function, they want us to find the x values of all relative extremes and justify our answer. So a sign chart's not going to be enough. We're going to have to spell things out. To find those relative extrema, we need to find critical values of this thing, places where this could be turning around, because those are going to be where your relative extrema live. So our first derivative of this, f prime, we've got 6x squared minus 6x minus 12, and then that 5 is just a 0. So let me set this equal to 0 and find critical values. In this situation, I can factor a 6 out of all these. That leaves me with an x squared minus x minus 2 inside. And then things that multiply to negative 2 and add up to negative 1, I can factor this into x plus 1 and x minus 2. So this equation then is going to equal 0 at x equals negative 1 for that first parentheses, and x equals 2 for that other parentheses. These are my critical values. I'm going to put these on an f prime number line. So we got negative 1 and 2, and I'm going to do some sign analysis to see if f prime is changing positive to negative or negative to positive anywhere. So testing a number that's less than negative 1, like negative 2, and I'll just use this version of f prime right here. So that's going to be a negative times another negative, which is positive. Between negative 1 and 2, we've got 0. That's a good number to use. So that's a positive times a negative, which comes out negative. And then bigger than 2, let's test out 3. So that's positive times a positive, which comes out positive. Now I notice that f prime is changing from positive to negative at x equals negative 1. Therefore, f has a relative max at x equals -1 because f is increasing and then decreasing at this spot. Now I also notice f prime changes from negative to positive at x equals 2. Therefore, f has a relative minimum at x equals 2. So this is the reasoning you need to show to really justify your answer. You have to talk about f prime changing sign in a certain way at these x values. For this one, we want to find the x values of relative extrema for this weird kind of hybrid function and justify our answer. Since we're starting with f of x, we're going to have to figure out f prime of x and see where critical values on that are changing sign. So to do f prime for this, for my derivative, I need the product rule. Let me use my box and ribbon to organize that. So I have two factors. I have 3x and e to the 6x, and their derivatives, which for 3x is 3, and we need a chain rule on e to the 6x. That's actually going to be 6 times e to the 6x, multiplying by the derivative of 6x. So now multiplying that out with the ribbon, I've got f prime equaling 3 e to the 6x plus, let's see, this will be 18x e to the 6x. And I need to figure out where this thing equals 0 or is undefined. Now we don't have to worry about this being undefined because exponential functions are known to be continuous, and so are linear ones like this 18x here. So multiplying one continuous function by another is going to give you another continuous function. So what do I do then to get the zeros? Well, I notice that these have a common factor, a few common factors. They both have this e to the 6x that I can take out. We can also take a 3 out as well. So 3e to the 6x. That leaves us with just 1 for this first term. This next one will be 6 and x. There's no more e in there. And all of that's going to equal 0. So 3e to the 6x, where does that equal 0? Well, an exponential function never equals 0, so we actually don't get any critical values out of that part. Over here, though, 1 plus 6x certainly does equal 0 somewhere. If you subtract 1 and divide by 6, that's -1 over 6 for that critical value. So that gives us something we can now put on our number line here, the f prime number line. We have -1 over 6, and we're going to test something on either side of this. So a number less than -1 over 6, well, let me test out -1. Plugging that into, I'm going to use this version of f prime. Now, when you're doing your sign analysis, this 3e to the 6x, since it's exponential, is always going to be positive unless there was a negative out in front of it. But by itself, it's always positive. So we don't even look at this first part. It's really just the 1 plus 6x that's determining the sign of this. So we have 1 plus 6 times -1. That's going to be a negative number overall. And then if I plug in something bigger than -1 over 6, 0 is a pretty easy one. I've got 1 plus 0 essentially, which is positive. And I notice here that f prime is changing from negative to positive at x equals -1 over 6. That means I have a relative minimum for f at x equals -1 over 6. On this problem, given this function right here, we're trying to find x values of relative mins and maxes for f of x and justify the answer. So these are going to be places where f prime is going positive to negative or negative to positive. However, if you look at what they gave you here, they already gave you f prime. So we don't need to take the derivative of this. In fact, that would give us the wrong answer. We just need to kind of accept this as it is, find critical values, and do some sign analysis. Okay, well, if I take a look at where this thing equals 0, I realize it doesn't equal 0 because we don't have a variable in the numerator. We have -1, so this is never going to be 0. However, this will be undefined. F prime of x will not exist if x equals 1, because that would be dividing by 0. So we have a critical value at 1 that we might need to put on a number line. Before you do that, though, let's do a little pre-sign analysis. -1, the numerator, that's always going to be negative because it's a negative constant. The denominator, x minus 1 squared, well, that's always going to be positive because you're squaring it, and squaring always makes things positive. If you have a negative over a positive, you're always going to get a negative number out of that. So if we just think about this a little bit, we notice that f prime of x is going to be less than 0, is going to be negative for all values of x other than the one that's going to make it undefined. So we don't actually need to do a sign chart for this. We already know this thing is negative pretty much the whole time. Since there is no sign change from negative to positive or positive to negative, no sign change for f prime means we're not going to have any relative extrema at all for f. For this problem, we're given the function f of x equals x plus 2 cosine of x on the interval from 0 to 2 pi, and they want us to find the intervals of increase and decrease and the x values of local extrema and which kind of extrema those are. So first thing we're going to do that would help us with all of this is to find the first derivative of this, because we're going to need to look at the sign of the first derivative for all of this analysis. So using our power rule and line rule, we've got f prime equaling 1 plus, and now the derivative of cosine would be negative sign, so this is actually negative 2 sine of x. And we need to figure out where this takes on a value of 0, because that's going to tell us where the sign is changing. So let me go to Desmos to graph that out. So we've got, I'll just call this g, equals 1 minus 2 sine of x. And I only need the interval from 0 to 2 pi. So I'm going to go to my wrench here and change my x-axis. And I'll make this go from negative pi over 2 to positive 5 pi over 2, or 2.5 pi. And I'll just make this go by half pi's. That'll just give me the window I need here. So now I can see between 0 and 2 pi pretty clearly. Now clicking on my function and clicking on the gray dots that come up, I see that I have an x-intercept at pi over 6 and also at 5 pi over 6. And there's one past 2 pi, but we don't care because that's outside the interval. Alright, so here is the picture I just drew. And now we notice again that pi over 6 and 5 pi over 6 are our critical values. And we also notice, since f prime is positive on the interval from 0 to pi over 6, that we have f increasing on that interval from 0 to pi over 6, and also on the interval from 5 pi over 6 to 2 pi, where f prime is also positive. So those are our two increasing intervals. The decreasing interval is the place where f prime down here is negative between pi over 6 and 5 pi over 6. So we're decreasing on that interval. Now, as far as the max and the mins go, I notice that we are changing f prime from positive to negative here at pi over 6. So f has a relative or a local max at pi over 6. And then we notice that f prime is changing negative to positive at 5 pi over 6. So there's a relative min for f at 5 pi over 6. For this problem, we are given f prime for a function, and we want to find intervals of increase and decrease and also local extrema. So normally to do this, we would take a derivative and then check out the sign of the derivative, but they've already given us the derivative we need. We want all of this information for f of x, and we already have f prime. So I'm just going to go straight to my Desmos calculator, graph this out, and do a little sign analysis. So we're going to see on Desmos that this takes on a value of 0 at, well, let's figure out where that actually happens. So on Desmos, let me just move so I can see my function. I'm going to call this g so I don't confuse it with f. And this is going to be fraction negative 10x squared plus 10 all over x squared plus 1, and then parentheses, and then square that. So this is the crazy function we're looking at, and they gave us the interval from negative 2 to 2. So I'm going to make my interval go from we'll do negative 2.5 to 2.5, just so I can see everything I need to. So there we are. My x-intercepts, if I click on the function and then click on the gray dots here, we've got negative 1 and positive 1, and that's it. So here's that graph. And I notice that since f prime is positive on the interval from negative 1 to positive 1, and those are our two critical values, that means that f is going to be increasing on that interval from negative to positive 1. And since f prime is negative from negative 2 to negative 1 and also 1 to 2, that means f is going to be decreasing from negative 2 to negative 1 and 1 to 2. As far as maxes and mins, we notice that f prime is going positive to negative at x equals 1,
and negative to positive at x equals -1. We'll do that one first. Since we're going negative to positive here, we have a local min for f at that spot. And since f prime is going positive to negative at x equals +1, f has a relative max at x equals +1.
This next problem is kind of a final boss battle of sorts. They're asking for an absolute minimum on a function that is not on a closed interval. So the extreme value theorem guarantees nothing in this case since we don't have a closed interval. The function itself is continuous, but that by itself isn't necessarily enough. So in situations like this, we've really got no choice except to find critical values, do sign analysis, and hope there's only one sign change for the whole function. If there is, then we can do something with that. Otherwise, we're out of luck. So let's find f prime. That's going to be 4x cubed minus 12x squared, and then the 81 is gone. That's just 0. So setting this equal to 0 and solving, we can factor out a 4x squared. That leaves us with an x minus 3 inside. And we see that this equation is true when x equals either 0 for that first factor or 3 for that second one. All right, let's put these on a number line and do some sign analysis. So this is an f prime number line. I've got 0 and 3 on here. Let me test something to the left of 0, like -1. Now, doing my sign analysis, I'm going to use this factored version here. And this 4x squared I know is always going to come out positive because I'm squaring whatever I put in there. So really, it's just this x minus 3 that determines the sign of the whole derivative. So if I plug -1 in this parentheses, -1 minus 3 is a negative. Now something between 0 and 3, I think 1's pretty easy. 1 minus 3 is also negative. And then something bigger than 3, like 4, 4 minus 3 is a positive. So I notice here that I've got an f prime that is negative or 0 the whole distance from -infinity to +3. So that means our function is either decreasing or at least not increasing until we get to x equals 3. And then f prime is positive thereafter. So that means our function is decreasing until 3, or at least not increasing, and it is increasing afterwards. So what does this mean? It means that I've basically got a local min at x equals 3, and since it's the only sign-changing critical value for my whole function, it's also going to be the absolute min. So the way I can justify this, writing it out here, I can say that f prime of x is less than or equal to 0. I have to use equals because I've got this one spot here where it actually does equal 0. So less than or equal to 0 for x less than 3. And f prime is greater than 0 for x greater than 3. Therefore, I know that my min, my absolute min for f is going to occur at x equals 3. This is great. I still haven't answered the question. They said find the absolute min. They mean like the y value at that point. So I have to actually plug 3 back into the original function here. So I need f of 3. So let's just do this out. We've got 3 to the 4th, that's 81. 3 to the 3rd is 27 times 4 is going to be 108, so we're subtracting 108. And then we still have this minus 81. Now, you could leave this unsimplified, but this is kind of convenient. I mean, 81, negative 81, those cancel. So really, negative 108 then ends up being your absolute min.